In the 1970s, the global manufacturing landscape fractured. Automakers in Detroit, who had defined mass production for decades, watched their market share erode as Toyota began producing higher-quality vehicles at a significantly lower cost. Market dominance resulted from a rigorously applied breakthrough in operations control theory, rather than a mere difference in labor costs or materials. This chart compares the productivity gap in its rawest form: heavy machinery setup time. To change the massive dies on a standard industrial press, American facilities required an average of 6 hours. Toyota achieved the exact same mechanical changeover in 10 minutes. That speed advantage scaled directly to the balance sheet, specifically in the turnover ratio of working assets. While an American automotive plant turned over its working assets roughly 6 times a year, Toyota operated at 63. The asset turnover ratio measures the efficiency with which a factory uses its equipment and on-hand inventory to generate sales. A high number indicates a system that converts raw materials into sold goods with almost no stagnant capital. The architect of this efficiency was Taiichi Ohno, vice president of Toyota. In 1977, he and his engineering team published a paper formalizing the mechanics of the Toyota production system. Toyota had built a mathematical system that structurally rejected the need for bloated capital assets and excessive machinery. To understand Ohno's system, we must examine the standard it replaced: push manufacturing. Push systems rely on centralized forecasting to dictate exactly what a factory should build over a given quarter. Planners create a top-down schedule, and each workstation on the floor is ordered to produce a specific quota. They do this blindly, ignoring whether the next station down the line is broken, backlogged, or facing a shift in customer demand. This localized overproduction guarantees massive buffers of partially finished parts, known as work in process or WIP inventory, accumulate heavily between workstations. Plant managers view these buffers as essential safety nets. If Station B breaks down, Station C can keep working by pulling from accumulated WIP. Toyota's engineers arrived at a radical counterdiagnostic. Work-in-process inventory is the worst possible waste a manufacturing plant can generate. They recognize that inventory is an obfuscation metric. Storing surplus parts hides severe systemic flaws, masking unbalanced assembly lines, chronic equipment failures, and surplus worker capacity. In operations theory, this is compared to a river. High water levels, representing high inventory, allow a boat to easily pass over jagged rocks. The rocks are the operational problems. The water simply hides them from view. As long as those buffer inventories exist, a factory operates without any mathematical or operational incentive to permanently solve its underlying inefficiencies. Toyota's engineering requirement was precise: operate a high-volume, highly complex automotive factory completely without the safety net of buffer inventories. The solution was just-in-time production. Every workstation would produce only the necessary parts at the exact required time and in the specific quantity needed. To execute this, information flow had to be entirely reversed. Instead of orders pushing down from the top, the final assembly line pulls what it needs from the preceding station, which then pulls from the station behind it. This backward flow is mediated by a physical signaling mechanism called a Kanban card. The operational loop works like this. A worker at Station 3 takes a conveyance Kanban to Station 2 to withdraw a specific part. Removing that part triggers a production Kanban at Station 2, authorizing them to build exactly one replacement for the part that was just taken. While Western factories were attempting to centralize scheduling with massive early computers, Toyota relied on printed cards. Physical cards provide rapid, precise, and highly localized facts about shop floor capacity without any data processing lag. By reversing the flow, the factory ceases to be a collection of isolated silos pushing blind quotas, operating instead as a single interdependent organism reacting instantly to physical reality. The Kanban system functions as a rigid mathematical control loop, far beyond simple visual organization. This is the equation that dictates the absolute cap on inventory allowed within the Toyota production system. The variable Y represents the total number of Kanban cards authorized for circulation. Because each card corresponds to a specific bin of parts, Y is the absolute mathematical limit on the system's inventory. The variable D stands for demand. For this equation to function without tearing the factory apart, demand must be mathematically smoothed. a process Toyota calls Heijunka. Spikes in production orders are leveled out to maintain a stable daily rate. The variables TW and TP represent the waiting time of the Kanban card and the processing time required to build the part. This exposes the mathematical trap of the system. If demand fluctuates or increases, the only way to keep the inventory limit Y from skyrocketing is to aggressively slash waiting and processing times. We can see the physical reality of processing time, or TP, in a piece of equipment like this massive industrial press. Changing the heavy metal dies for different parts is the primary bottleneck. Toyota engineers systematically attacked this exact physical bottleneck. By engineering quick change dies and modifying the machinery, they forced TP down from hours to minutes, keeping the equation balanced. But the ultimate forcing function of the entire operation lies here, in the Greek letter alpha. Alpha is a policy variable. It is a dial controlled by management that represents a specific workshop's capability to handle interference. As alpha decreases, the total number of cards, and therefore inventory, shrinks. Management intentionally dials down the alpha variable to remove cards from circulation. This deliberately starves the assembly line of buffer inventory to expose hidden bottlenecks and force breakdowns. Kanban is not a tool to manage inventory. It is a mathematical vice grip used to artificially induce stress, forcing engineers to eliminate waste in order for the line to survive. Running a factory with zero inventory buffers creates immediate and extreme operational fragility. Without work-in-process inventory to fall back on, a single defective part or localized machine breakdown will instantly ripple downstream, halting the entire final assembly line. To counteract this extreme fragility, Toyota implemented a required engineering countermeasure known as Jidoka, or automation. Jidoka dictates that equipment must be designed to automatically stop the exact moment an abnormality or defect arises. If a part misaligns, the machine instantly freezes in place. It physically halts the process to prevent the defect from continuing downstream. Jidoka prevents the system from making the worst waste even worse. It ensures the factory never spends time and energy overproducing defective parts. This principle of immediate halting extends directly to the human workforce. Every worker on the floor is given the authority and the obligation to pull the andon cord or press a stop button the moment they detect a problem. Jidoka fundamentally shifts the factory's goal from keeping the line moving at all costs to stopping the line to expose the truth. This systemic transparency leads to the final component of the Toyota production system, the respect for human pillar. Zero buffer manufacturing creates an environment where delegating absolute authority is a strict operational necessity. Because a just-in-time system is too lean for top-down oversight, the factory floor must rely entirely on the intellectual capability of its workers. To Ono, respect meant acknowledging that the shop floor worker is the only person capable of reacting to solve a line stop in real time. This requires visible control, making the workshop's status so transparent that every employee possesses the same high-level data as a manager. The tight Kanban limits create constant pressure to solve flaws. This pressure forces workers to transition from repetitive labor to active problem-solving, engineering permanent solutions just to maintain the flow of the line. This chart illustrates that cultural shift. Between 1965 and 1976, Toyota worker proposals climbed from 9,000 to 380,000. These were rigorous engineering fixes, evidenced by an 83% acceptance rate across submissions. The Toyota production system succeeds because it replaces the illusion of centralized push control with a decentralized, mathematically enforced ecosystem of continuous human ingenuity.